Oh, okay. Hello, everyone. So first of all, thank you. Thank you for coming to my talk. There are a lot of beautiful talks. There are a lot of amazing speakers here. So thank you for picking my talk. Ciao. I'm Edoardo. I'm Italian. This is my first time here in Malmo, lovely city. I'm a dev at Storyblock. Storyblock is a headless CMS. You can find our booth. So if you want to come say hi, we are somewhere down here. And I live in Bologna. Do you know where Bologna is? How many of you know where Bologna is? Oh, some of you know. So Bologna is here. So it's right below the Roman Empire. And this is like a view of my city. So the two towers you see here, they are the symbol of our city. This is another view with the big square and the big church. This is a lovely view in the city. This is something I love, which is like hidden corner in the city with a canal. And these, of course, are some of the things that you will love and that everyone comes to Bologna for. So like porcelain. Now, what are we talking today? I want to talk to you about compression. Compression algorithms and especially compression in HTTP, so in the web world. If we have time, but I don't think this will happen, we will do some Q&A and some bonus content in the end, but I have tons of slides, so probably that's not gonna happen. Why I thought about this presentation? So we are a SaaS, so we are a software as a service. We serve a lot of content. So we have a CDN. We serve assets. We serve assets. And so these are some of our numbers. So every month we serve terabytes of content, right? Terabytes from the CDN. They're JSON files. So tons of gigabytes of JSON files. And also tons of assets. And so compressing data for everyone who's serving data through the web is fundamental. And we have to better understand how compression works, what compression formats are available to use in the web, and maybe what are their basics, like what are they built on. And I started to think about this talk, and I wanted to like have some hook to the sci-fi because I'm a huge sci-fi fan. So how many of you have watched this movie, Honey, I Shrunk the Kids? Not all of you. So if not, you should absolutely watch it because it's a classic. And it's a nice movie, a Disney movie with the great Rick Moranis. And so in this movie, basically, this scientist invented a machine to shrink things. But accidentally, he at some point shrunk his kids and his neighbor's kids, right? So, okay, this is the story, but I like to like ask questions when I see or read sci-fi things. So the questions can be like, is this possible? Is this scientifically possible, scientifically accurate? So you can ask many questions. For example, there are questions regarding the laws of physics, like the conservation of mass and energy. So when you shrunk something, where are all this mass goes? So it needs to be transformed into something. But then, of course, you need to restore it. So you need to also maintain, like keep the entropy to reverse it. So it's not that easy. And if you want to like build a machine that shrinks objects or human beings, what would be your strategy? So every time you want to solve a problem or you want to invent something, you need to think about the strategy. So every step that you need to take in order to reach your goal. This is an algorithm, by the way. An algorithm is just a series of steps that you go into to do something, to reach your goal. Of course, you need to prevent organ failures. You need to think if you want to like shrink every dimension or just eliminate things. But then you think about it, if you eliminate things, then it's not the same thing. It's not the same human being if you just take away molecules or organs, right? And so there are many problems. But as the great Carl Sagan said, science is not just this body of knowledge. It's a way of thinking. And I love to use this material to think about, to ask questions. So in this movie, you have this shrinkage of human beings. And the main feature of these kids is that they are identical. Like when you have the normal size and the molecule size, they're identical. It's the same amount of information. So this is lossless compression because you don't lose information. It's the same amount of information. And spoiler, in the end, it's a Disney movie, so in the end, there's an happy ending. So in the end, they reverse the process and they have their kids back to the normal size. This is called bijective function or perfect reversibility. So you apply the same function in reverse to your input or to your output and you get the same input. So it's bijective. And again, you lose no information. This is lossless. So in lossless, you don't lose information. All the lossless algorithms are bijective. And with lossy algorithm, then you lose information. And you can never recover them. You lose them forever. A cool example and a simple example of a lossless algorithm is the run length encoding algorithm, RLE. And it's great because you see like one of the main features of these algorithms, substitutions. So this is up here, this is the original data that you have, original string. And down here, this is the compressed string. So what's the relations between the two? You see, here you have a sequence of characters, and here you have another sequence, but here you have 3 times b. So the key here is to think, how can you substitute this pattern with another one, keeping the same amount of information but with less characters. So the idea is, okay, instead of writing b, b, b 3 times, I write 3 and then b. So I know that there are 3 times b, but I use just 2 characters, so I save 1 character. So you do this for every pattern that you have in the original string, and then you have a compressed string. This is key for basically every lossless algorithm, substitutions. So you need to represent the same information that you have in input with something in output, replacing the way you the picture information, the way you represent the information. And this is a cool example. This is, of course, you may think this is too simple, it's not very effective, but actually it is effective. It was used in the PCX, for example, image format, and also in some fax formats. But you can imagine if you have like patterns that repeated and consecutive patterns repeated often, this can be quite effective. But what is really effective nowadays is this algorithm, which was like invented by David A. Hoffman in 1952, the Huffman encoding. Huffman encoding is still about replacing tokens, replacing symbols, but it's quite more complex. So the key thing is that you want to go from this string to a representation of these strings that uses less information that you would need without compressing it. So when you want to represent a string of bytes, a string of characters, you need a minimum amount of bits to represent it. And you can calculate how many bits you need to represent it, because if you take the whole UTF-8 character map, you know that for each character you need at least 8 bits, right? But to write this string, you don't need all the characters in the table. You just need the characters that are present in this string. So Huffman coding is clever in this way. He tries to represent, to build a structure that represents all the characters that you have in this string, not all the possible characters, but just what you have in this original string. Then he builds a structure, a binary tree. So when you want to decompress this into the original format, you just take your tree, you traverse your tree, and then you have the original format. Okay, I'm not explaining to you the whole algorithm, but it's pretty simple. The idea is to have less bits for representing the same amount of information. And this is Huffman coding, and this is key, and this is the foundation of basically every compression algorithm that we are using nowadays, lossless algorithms. Another key piece of the lossless algorithms is LZ. LZ version 77 and version 78 by Lempel and Siv. Again, it's about substitutions. So up here, the original string, you have repeated patterns. So the idea is, okay, I find that there are repeated patterns in my string. I substitute the patterns with tokens, 2 tokens actually, because you can see that if the patterns are repeating, then I can go back to the original, to the first time that I see the pattern, and just have a pointer to that symbol. So in this case, I have ABC, ABC, repetition. So I substitute the second time I see ABC with a token. 3 is how many bytes do I have to go back. So 3 bytes, I go back to A. And the second token is the length of my symbol. So 3 bytes back, 3 bytes the length. And so I can substitute this with a pair of tokens. And the same I do, I go with ABC, ABC, another pair of tokens. 6 back, 6 is the length. Again, substitutions. Less bytes, less bits to represent the same amount of information. Now, when you want to have an effective compression algorithms or format nowadays, you try to combine the algorithms that you have. And you may remember, if you are old as me, you may remember that in the 90s, we used to have this wonderful software, Gzip. And Phil Katz, actually, Gzip is for Phil Katz. And I discovered this just studying for this talk. I didn't know that. But Phil Katz is actually the author of Gzip. And he combined LZ and Huffman. So first, in this algorithm, in this format, he applies LZ, and then he applies Huffman to LZ. So a double encoding, and then you have compressed data. And this algorithm, so this combination of the two algorithms is called deflate. And you will find, again, you will find deflate in many compression formats. For example, Gzip, zlib, they are all based on deflate. And it's this thing. So you deflate and you inflate by applying the same algorithms in reverse. And another very important families of formats and algorithms are dictionary-based. And here the idea is, okay, in my original data, in my original text or whatever, I have patterns that are repeating. I have symbols. I have words. So what if I make a dictionary, static dictionary, and I substitute my words with pointers to that dictionary? Then I can, again, represent an entire word or symbol with just a pointer, some bits, to point to the static dictionary. So of course, then I need to share the dictionary between the client and the server, but the dictionary is quite small. So there are many algorithms based on this technique. There are algorithms based on static dictionary, so the dictionary is pre-made and shared between clients and servers. There are dynamic dictionaries, means that they are built at runtime while the algorithms is analyzing the input data. And there are pre-trained algorithms, pre-trained dictionaries, where you build a dictionary based on the data that you have. So you analyze all your data and you build a dictionary based on your data. All these algorithms families, all these lossless algorithms are necessary when you want to transfer data on the web that, of course, you can't lose information with, like text files, coding, structured data. So if you are dealing with an API, you want to transfer JSON, or you want to compress JavaScript, HTML files, you can't lose information. You need lossless algorithms, right? Instead, with lossy algorithms, you lose data, and again, you will never recover that again. And lossy algorithms are based on like tricking the human perception. Like if you see this JPEG compression, the first image is compressed around 30%, if I remember, 20 or 30%, and the last one is 80, 90%. But you can't really tell the difference. There are differences, of course. You may maybe see here, there are some differences. But look at how many bytes you spare in this case. And so you lose, again, when you compress like this and you have this compressed file, you can't reconstruct the data that you have here. So you lose this information forever. But for many data format, it's fine because it's just good enough, right? So for many formats on the web, from JPEG to MP3, WebP, whatever, you just compress, lose information, and it's good enough. Now, let's go to the core of this talk, HTTP. So HTTP is like a beautiful protocol for transferring data on web. It's based on client and server. So the client requests for a resource, and the server responds with that resource. It's an application level protocol, and it's based on TCP. Well, actually, now version 3 is based on QUIC and UDP, but basically it's just a connection between two, like a client and a server. So request and response. So what are the problems here? The performance, so the speed of this connection, and the bandwidth, so how many bytes can you send? And the solution here is we can use compressed data. If you request data, so if you are a client, like a browser, and you request data, and you want that data to be compressed, in HTTP, there's a header here. It's called accept encoding. And you basically say to the server, hey, I want you to send me this data, and I accept these compression formats or algorithms. So in this case, yeah, Gzip, BR, I accept these formats because I'm able to reconstruct, to decompress. And so, welcome to HTTP compression. First is Gzip, because it's the most widely used and adopted. It was created by Jean-Luc Gailly and Mark Adler. It's part of the GNU project, so it's fully open source. And it's based on zlib, which is an abstraction of deflate. If you remember deflate, so zlib is basically deflate. And it is widely adopted. So virtually every computer in the world supports Gzip. And it's actually quite good. So you can get to 70 or 90 compression ratios for text files. It's quite good. And to show you like a quick round trip between the browser and the server, so it looks like this. Let's imagine that we have Nginx here on the server. So on my server, I can say to Nginx that I'm supporting Gzip with Gzip on. If the browser asks me a resource with this header, accept encoding Gzip, then the server is actually supporting Gzip. So when the server gets this request, it calls Gzip, like the software, to compress the data, and then sends the compressed data back to the client with this header, content encoding. So the header to request something is accept, because I'm accepting these encodings, and the header that you get back from the server is content encoding, because the payload or the assets that I'm sending to you is encoded with this compression format, Gzip. So when the client, the browser or whatever, gets this data back, it knows that he needs to decompress with Gzip. So it calls Gzip, decompress the data, and there you go. If you look at the Gzip format, you will see that you have the header. So the first part of the file is a header with some metadata so that you know what is in the file. Then you have all the compressed block with deflate, compressed with deflate. And then you have a footer for the CRC or Adler checksum, right? Now, if you remember that why we were talking about compression algorithms on the web with that repeated patterns and why they are effective, because why they are effective if you have a file that is made of repeated patterns, you also may understand why this is ideal and is actually pretty good for the web files. Because in a web, you have high redundancy. So in HTML, in JavaScript, in CSS, you have many repeated patterns. So even algorithms that are old, like Huffman, LZ, these are pretty good on the web because formats have high redundancy. And so this is the most widely adopted algorithm on the web. Now let me introduce you to this thing. This is what the Swiss call Brotli. So it's just small bread, but they call them Brotli. And someone at Google at some point decided to call their compression algorithm Brotli. I don't know why, but they decided just to call them Brotli. Maybe because they are small breads, I don't know. But actually, Zoltan Sabatka and his team decided to create this algorithm, Brotli, this format actually. This was designed in 2015 as a modern alternative to Gzip. is still based, as you can see, on LZ and Huffman, so it combines, it uses deflate. But then it applies a context model, and if you are now familiar with machine learning or LLMs, you may know what a context model is. If not, sorry, but I don't have time right now. But then you have a static dictionary. Then this is actually the core part of Brotli. You have a static dictionary that's optimized for the web. With Brotli, you can get to an output that is 10 to 20% smaller than Gzip. But the compression, so when you actually are compressing your data, that part can be slower. We talked about the dictionary. The Brotli dictionary is a static dictionary. So someone built that dictionary, and it's available for everyone, around 120 kilobytes. And in that dictionary, you will find common web strings. So div, function, whatever. And as we said, in a dictionary, you replace the patterns, the symbols that you have in your original file with just pointers. So look at this. For example, if you have script, you just replace the old script symbol with just a 5 bits code, a pointer to the dictionary. So this is perfect for text files, especially on the web. Not good with binary files, of course. You have 12 levels of compressions. So the higher the level of compression, the slower is the compression. So of course, for CDN, you just use this. You use the higher level because you compress everything at build time. Then you put everything statically on the CDN. But this is also optimized for HTTP2, HTTP3, the streams. So of course, you need to balance between your compression ratios and the performance that you want to have. And if you want to use Brotli, the header is BR. So the symbol is BR. So this is actually can be better than Gzip. So be sure to use BR. You can specify multiple formats. So if you make requests and you want to accept multiple encodings, just put Gzip and BR. They are good enough. And most servers support them. And since Google made them, they are virtually on any browser since Chrome in 2016. So it's everywhere. And this is the static dictionary, not all the dictionary, just a couple of pages. But you can find it here. There's an RFC, so you can download it in TXT. It's a binary dictionary. You can actually provide your own dictionary. So if you have very specific data that you understand, that you know, and you want to build your own dictionary and you want to use it, then you can build your own. The algorithms support custom dictionaries. So you can build one and provide one to your algorithms. Last but not least, Z standard or Z standard, I don't really know. It was created by Facebook the year after, so in 2016 by Jan Collette and his team. And Z standard is designed for real-time use, so real-time streams, chunks. Again, it's based on LZ77, but this time we don't have Huffman. We have finite state entropy, which is something quite complex, plus, optionally, a dynamic dictionary. So a dictionary that is built while the compression algorithms is working, so while it's analyzing your data. With Z standard, you have the speed of Gzip, actually it's faster than Gzip, and the compression ratio is close to the higher level of Brotli. Finite state entropy is quite complex. I cannot explain, even because maybe I don't really get it, but it's mathematics. It's based on asymmetric numeral system. It's like a mathematics system made by Jarek Duda. Using this technique, they are able to have like a substitution with a structure that it's not the binary tree that if you remember Huffman, in Huffman you use a binary tree. This time you use a table. You use tables. So basically the algorithm is close to Huffman, but instead of binary trees, you have tables. Why tables are faster than binary trees? Maybe if you have time for the Q&A in the end. But they can be faster. In many scenarios, they can be faster. The lookup can be faster. So with this algorithm, you have something that's nearly as compact as Huffman, and it's faster. encoding and decoding are faster. Oops. Again, here in Zstd, you have a dictionary. It's optional. You can use a dynamic dictionary. You can provide your dictionary. You can also pre-train your dictionary. So if you use the command line Zstd tool, you can train. For example, if you have an API, you have all your JSON, so you have static content, you can just create a dictionary pre-trained with all your data. And when you have a dictionary, of course, you have to then share this dictionary between your server and your clients. But then when you have it, the compression and decompression are really, really fast. So Zstd could be the new king because it's faster than Gzip and it's close to Brotli ratio of compression. It's ideal for databases, for games, for Linux. It's actually in the Linux kernel. And it's ideal for HTTP3 and streams. Again, a new header here, ZSTD for content encoding. But the problem is that Gzip is everywhere. Gzip is in every machine virtually. And it's good enough. So you have 70 to 90% compression. It's good enough. And Brotli, if you have the highest compression rate and the static dictionary for web files, so HTML and JavaScript, CSS, it beats Zstd. So in the web, most of the time, Brotli is still better. And in order to get to the higher performances with Zstd, you need to pre-train the algorithm on your data. So in the end, probably Zstd is the best one, but in practice, everyone uses Gzip and Brotli. Also because Brotli is pre-installed in every browser, because is in every Chrome browser, and Gzip is virtually everywhere. But I also suggest you to follow the Meta engineering blog, because the Meta engineering blog, because Zstd was created at Facebook, now it's Meta, right? Meta is working on enhancing the compression algorithms that they have, and they released a couple of weeks ago or a month ago a new standard which is called OpenZL, something like that, which enhances these concepts again. So they are really working on compressions. So what I wanted to say, we are building on algorithms that we know, that we created in the 50s and we then perfected in the 70s, 80s, but we are still building new compression formats. And for web performances, they are good. And actually, I wanted to also, I won't have a Q&A section, I'm sorry. I want to have some bonus content for you, because I wanted to go deep into some technical bits of what I said about LZ and Zstd in particular. Because if you remember, when we talked about LZ, we talked about substitutions in our original string, like we substitute tokens with, we substitute symbols with tokens, right? But the problem is, in the original deflate, we needed to split the original data in chunks of 32 kilobytes. Why? Because of the hardware of the time. So we needed to use these algorithms in these chunks, and then we need to go to the new chunk. We could not go back. Why? Because memory constraints at the time and the implementation were simple and it was good enough. But now, in Zstd, zlib is enhanced because now we don't have memory constraints, so we can go to 1 megabytes, we have longer buffets, we can use rep code modeling, which is something that substitutes symbols in a more effective ways, so we can further compress. And Cloudflare actually is working on even enhancing LZ, so if you go to the Cloudflare tech blog, you will find some articles on enhancing the LZ compression. Of course, for Cloudflare, this is really important because they serve data. Also, when you are dealing with HTTP streams, you need to understand that in streams, you compress data in real times, and you have chunks of data. So you cannot really compress everything at build time and then serve them statically. You have to compress them in real time. But there's a trick. because web streams are predictable. So when you stream HTML or you stream JSON, you can predict what would be the next symbol, the next character. So for example, in a HTML text, after H, it's very likely that you have 1, 2, or 3. So this is what you can use, why you can use the context modeling to predict what will be the next symbol. And if you can predict the next symbol, then you can have a better algorithm that can pick the next symbol faster, right? And Zstandard was designed to handle streaming. So if you look at the code of Zstandard, all of these algorithms are open source. So you can go to GitHub and check their code. If you look at Zstandard, you will see that they have a specific function for dealing with chunks. So everything is ready for chunks. And last thing I promise is the problem of branch prediction that got the meta-engineerings to substitute the Huffman tree with tables. Now, I said that if you instead of the binary trees, you use table, then the lookup is faster. Why? Because you have, in modern CPUs, like in every CPUs, you have the problem of the branch prediction. Problem is, when you have conditional branches, the CPU guesses what would be the most likely branch. And this guess is done by the branch predictor. And it's very important that the CPU predicts the next branch correctly, because otherwise you have to stop and flush your cache and go again. So it's like low-level stuff, but the branch predictor is highly important. So because again, if you mispredict, you have 10 to 20 cycles CPU loss. So why a branchless execution is important? Because you don't have branch that you can lose. With binary trees, you have branches, because binary trees are left or right, so they are branches by definition. With table lookups, you don't have branches. With table lookups, you can use techniques, you can use programming techniques or mathematical techniques to avoid using branches, like bit masks, predicated logic. And they are also more friendly with modern CPU instructions like seamed instructions. So that is why Zstandard adopted finite state entropy, because finite state entropy is branchless. It uses jump tables, and so avoids function calls, avoids branches, and is faster. It's faster than modern CPU. That is why Zstandard is so fast. I know that I killed all of you today, but I got to the conclusion finally. So compression on the web is crucial, because you have data that you want to transfer, and you want to compress that the more you can. And high load times affect sales, because you have to pay. When you transfer data, you pay. You pay for the amount of data that you transfer. Today, Gzip is the king, because it's everywhere, it's ubiquitous. But Brotli follows. So be sure that every time you request data on the web, at least in accept encoding, you should say GZ and VR. But Zstandard is incoming, and again, Meta is working on new algorithms and new formats. But all these new algorithms, they are working on something with static dictionary or pre-trained dictionaries. So something around the concept of dictionaries. So dictionaries are the present and the future of compression algorithms. So if you want to study them, look into dictionary-based algorithms, because they are like present and future. And I finished. So thank you. You can find me online. These are my handles in any, thank you. These are my handles in YouTube, LinkedIn, and Mastodon. Thank you. Now, I think we also have some time for some questions. Thank you. Was I too fast? Was I too fast? A bit too fast? No. Do you have questions? Or was I able to like kill every like little bit of interest that you had? No questions. Oh, questions. One. I don't get. What do you mean? Mm-hmm. It's not that there's no need, it's that you really can't compress binary data. Like it's very hard to use lossless algorithms with binary data. So it's really, if you have something that's already encoded with binary data, that's already encoded in binary, then it's really hard to compress. Like if you try to take a binary file and compress it with one of those algorithms, you will see that the space you save is none, basically. So with binaries, you don't compress. You compress with text files, strings and chunks, streams, whatever. Okay? And I don't know if I answered you. Okay. Yeah, but you have abstractions. So it's true that you have, like the branch predictor is unique for each CPU architecture, okay? But you have abstractions. So you really use that abstractions that then should be able to translate your algorithms for the architecture. I don't know really what's the difference between the branch predictor in ARM and the branch predictor in Intel. I don't really know, but I think when the compilers take care of the branch predictor translations for you, like the branch predictions the branch predictions happen at compile time when you compile and at execution time. So you don't really care what CPU are you using unless you're writing a compiler, basically. So it's the compiler that should understand which branch predictor is he targeting, right? There's low-level instructions. At higher level, you have abstractions. So the concept should be the same. The implementation should differ, but that's the compiler problem, I think. Yeah. We serve JSON for API calls. So when you call the API, you get JSONs back. But if you use the assets bucket, then you get assets. So we use lossless algorithms for JSONs, lossy algorithms for buckets, for the assets. So we use both, basically. But yeah, with JSONs, you can really compress JSON because they are predictable, they use many repeated patterns, and also you can pre-train your dictionary on the JSONs you have because you know the formats of your JSONs, right? So you can train your dictionary, you can create a dictionary. You ask, basically. When you make a request, you use accept encoding BR. When you get your data back, you will see content encoding. If BR is in content encoding, then you know that the server supports BR. That's why you should not just specify one compression format. You should actually specify all or the compression formats that you want in the order that are better for you. So the first is like the first you specify is the more likely to be the most likely to be used on the server. So if you say like I prefer BR, so you put BR first. Then my second choice is Z standard. You put Z standard. Then my last choice is GZ, and you put GZ. So the server will process them in that order. So if the server supports BR, then it will compress with BR and sends you BR. But you only know when you get your response. So use that sequence, okay, in the order that you prefer. No more questions. One. Okay, it's always a balance between the amount of data that you want to serve and the time that's needed for you to compress that data. So typically, when you respond with the JSON can be quite big because even if you just have a JSON that represents just a single endpoint, but it can be quite big, and usually compressing that JSON is faster than the amount of time that that takes to send the whole payload. The thing now is, what's the best balance? It's best to compress with Gzip and then put it on a CDN, or with Brotli put it in a CDN, or stream it. Streaming can be good, but streaming needs a stable connection. So you have a trade-offs basically, and you must test. You must test your CDN, you must test your API, and see what's best for you. Typically, if you can predict if your API is highly predictable, probably Brotli is good enough for you because you have a dictionary which is fixed and it can be quite fast. Oh no, it's just well, it's not hard to provide because it's when you compress, it's just a parameter that you pass with your static dictionary. The challenge here is that the client must also have the same dictionary. So you somehow must send this dictionary to the client, and they must take this dictionary and pass it to their function as parameter. So you must know your client. So if you control both the client and the server, then it's easy because you share the dictionary and in your pipeline you use the same. But if you don't know your client, then it can be challenging because you then have to send the dictionary with your data, and you have like 100 or 200 kilobytes more. So if you don't know your customers, your clients, you can't really use a custom dictionary. If you know them and control them, then yes, you provide a dictionary, you share them with them, and that can work. Yes, yeah, you should not do that. Yeah, in web browser. Yeah. Okay, we're done. Thank you, guys.